Thank you for joining this webinar. This webinar is focused on how to find stories in your survey data. For those of you waiting for the next in our series of conjoint, it is next week. As always, I'll present from within Displayr, but much of what I show you today can be done in Q as well. Please type any questions you've got into the questions field in the GoToWebinar app. You may need to click the little orangey red box with the white arrow in it to see the fields. I'll get to them at the end of the webinar, unless you're saying, hey, the audio is not working or something. The first step in finding the story in your data is to create and implement an analysis plan. Typically, this involves the creation of hundreds or thousands of tables of data, and that's the easy bit. Then the next stage is to reduce all the data so that all that's left is the interesting stuff. This second stage, known as data reduction, is the main focus of this webinar. It's a natural thing when you've collected data to just jump in and play with the data. However, as a pretty general rule, when people do this, they just end up getting lost. They don't find a story. The smart way to proceed is to create a written analysis plan. There's something about writing analysis plans that focuses our minds. As an example, we'll look at an analysis plan for a study investigating the appeal of this product, the eye lock. I'll give you a moment to read the description. This is an example of an analysis plan. Don't worry if some of the jargon is new to you. We'll cover some of it in this webinar, and others are covered in some of our other webinars on doing data cleaning and creating crosstabs. And we'll send you links and share links to that later. Now, the key bit, and what we're focusing on today, is the bottom right-hand corner, which are the planned analysis and visualizations. As I mentioned, the most important thing is this key planned analysis where you think through what your goals are and come up with a plan. And it's always going to be specific to your study. There's no generic planned analyses always have to be done. Now, it's also always a good idea to identify the key questions in your study. And in this study, there's just one, question 14, which asks people how likely they will buy the product, and cross-tab it with everything else. Such exploratory analyses uncover insights that you didn't anticipate. And we'll focus on that today. Looking at the planned analyses in this study, with the eye lock, we're crucially concerned about whether they said they'd definitely buy the product. It's the kind of metric that commonly used for kind of tech studies. And the second table shows us what they said when they were told how much it was going to be. And you can see here that basically the purchase intent didn't change for the top box score, and we told them about price, but for some of the lower levels of intention, it did. The other key planned analysis was looking at correlations of other data with purchase intent and its price. We're not going to talk about that because we're going to focus on the exploratory analysis. There's quite a few tables here. You can see them all. It would take quite a while to read through them all. Lots of tables means lots of data. And this is where the job of finding the story gets hard. We need to perform data reduction. As the name suggests, the goal is to reduce the amount of data, chucking away all of the noise, so that all that's left is the story. The Pope of the day asked Michelangelo how he'd carved this most famous of all statues. He said, "It's simple. I just removed everything that's not David." And this is precisely how we find the story in our data. We remove everything that we don't know is interesting to our stakeholders. By reducing the quantity of data, we distill and concentrate it, so we end up with a much stronger flavor. For those of you that like your Vietnamese and your Thai food, it's much like the fish sauce. So how do we do it? but it's not as simple as getting a whole lot of fish and boiling them down. There are 8 key techniques to master, and they can be mixed and matched in any order based on what you're doing. We'll start with the first of these, which is to delete uninteresting analyses. My exploratory analyses, as I showed you before, consisted of a whole heap of tables with everything crossed by how likely they said they would be to buy the ILOC. So we've got all of these tables that you can see on the page now. Let's look at the first table. This table compares how long it took people to answer the survey questions by their purchase intent. It's hard to imagine a less interesting table. Now, we could just delete it because this first data reduction stage is just to delete junk. But with exploratory analysis, we can entirely automate the process. Statistics has invented this wonderful tool of significance testing, which is perfect for exploratory crosstabs. I'm sure many of you are familiar with it. The basic idea with your exploratory analysis is if there's nothing statistically significant, you just delete them, and you can automate it, as I said. So I'm going to select the folder that contains them all. I'm going to go delete, and I've got these options for deleting tables or pages containing tables. Now, a lot of people like to delete at the 0.05 level, the 95% level of confidence, but I was, as a researcher, a very lazy researcher, so I really didn't want to look at stuff unless there was a lot of evidence. If I'm doing exploratory analysis, it is a different story for planned. So I like to delete at a very high 0.001 level or low. And as you can see, we've got rid of lots of those tables, so our data has been reduced. Now, let's take a look at this table. What can we do to reduce its data? There's quite a lot of data here. There are 18 rows of numbers. There are 8 columns. So all up, if my math's right, it contains 144 numbers. So how do we reduce that? Well, the first column is based on people who are under 18, which there are none of, so it's just junk. We delete it. Now, most of the time in market research, we're only interested in the column percent. So if we want other statistics, we should put them on. That is, we shouldn't, by default, look at tables with all of these statistics. We should just have the column percent. All right, so now we've simplified it quite a lot, haven't we? What else can we do? Well, if you look at this table, the most thing that jumps out at you is the blueness of the column headings and the row headings. So let's simplify that a little bit. Let's change to a table style, which is completely blank. Similarly, the percentage signs are redundant because every number's got them. So we'll turn them off. To use some jargon from the olden days, we improve things by reducing the amount of ink on the page. It just makes the data easier to find and see. But there's still more we can do here. Notice here, if we look carefully, I would not buy is the top row, and there's a very clear pattern where we've got the I would definitely not buy is highest amongst the young people. The older they get, the more it declines. But there's another guaranteed pattern in all tables where you've got a question like this with mutually exclusive options. And that is, if the numbers in one row are high, then the numbers in the other rows will be lower. And that allows us to get rid of rows because we know they're just going to tell the basic story just in a different way of rows above. So I'm just going to hide them. This net row contains hundreds. I don't need that. This column over here is just showing me the overall score. I don't need that. So we've reduced it quite a lot, haven't we? What else can we do? Well, the significance tests aren't really adding much here, are they? Because the pattern's now so clear, we don't need a significance test to call it up. So it's just another form of junk, and it's gone. So deleting uninteresting analyses reduces the amount of data. Removing clutter, which we've also just done, reduces the amount of data. The next thing is to merge together similar things. Now, we could leave the data as is. I think we've actually simplified it sufficiently, but let's have a go at merging. Is 21 and 25, they're not such big numbers if we merge them together. Let's rename it. And we'll keep doing that. And so the cool thing is now, we started with 144 numbers, and now we've only got 3. It's a true reduction in the amount of data. The story is really clean to see here. The next data reduction technique is to change the scale of the data. Market researchers often call this recoding. As an example, some fool, that'd be me, has a few too many income categories here. It's very hard to get any real feeling for what the income is looking at this. Maybe we'd go, well, $50,000 to $60,000 is the biggest one, but not so good. So what do? Well, we're going to find the income variable, and then we're going to insert a new recoded variable. We're going to choose this awesome little option called numeric variables from code category midpoints. It adds a new variable. I'll drag it onto the page. And just to make it clear that it's dollars. And so this is telling us that the average income is $63,000. So that's a much better summary of all of this information, isn't it? Now, how did it do it? Well, what displayed in the background is kind of cool. It went through and it read through the labels and put the midpoints in when calculating the average. For the under 1,000, it was smart enough to go maybe 500. 200,000 or more, smart enough to go 225,000. And then the don't know and I refuse this question, smart enough to leave them blank. Some people get a bit nervous about this kind of thing, going, well, why is this 16,249.5? Why not 16,250? The good news is psychologists have been doing this type of recoding for about 70 years, and they've worked out it makes no difference. It doesn't matter what numbers you put in. All the kind of conclusions you get tend to be the same unless you do something really, really daft. These are the most common ways of rescaling or recoding data used in survey research. The ones in blue are the particularly commonest ones. Replacing our income categories with an average both involved recoding of the data via the midpoints and computing the average. And the average is technically a summary statistic. So we've started on this number 5 strategy for data reduction, which is to replace data with summary statistics. Now, all market researchers and survey researchers are already familiar with this because we replace the raw data with percentages and averages, which is the biggest and most useful way of summarizing data. But there are many other ways of doing it. Here's the most common summary statistics, and again, the ones in blue are the ones we use most in market research. Let's do a good big example. I've got a table here with, look, it's got horizontal and vertical scroll bars, and in total it contains 1,622 numbers, percentages. No one can read them all. This data is showing how frequently people viewed various TV shows, Doctor Who, Fargo, in these different categories. And it's a crosstab of all of this data by itself. It shows us the duplication or overlaps in viewing behavior. And it's really interesting information strategically, this type of information, because it allows you to do content planning, which types of programs should we create to compete with which others, and allows you to place it in advertising. So some fundamentally interesting data, but this table's too big to read. How do we do it? Well, one approach would be to have separate tables, one just showing Doctor Who by Fargo, one showing Doctor Who by Little Fires, and then we end up with something like 50, I can't do the math in my head, separate tables. So that would take a long time. But the better play is to change the data from being categorical to being numeric. And that's to do with how Displayr and Q work. And when we do that, and we're going to do it, we choose the actual underlying data, change its structure from ordinal to numeric. What'll happen is now Displayr is going to compute the correlations between each of the programs. And so we've gone from 1,620 numbers down to 121, which is, of course, a huge saving. And now, this massive amount of data your brain can read. Have a look. What's the key pattern you can see? And that's exactly right. There's lots and lots of blue arrows. Everything is correlated with just about everything else. And I'm sad to say this is true for me. I've watched all of these shows except for the one called You. Now, for those of you that are new to correlation, it's a wonderful little metric. A 1 means two things are perfectly correlated, which is to say you can predict viewing of one show by viewing of another show. A score of -1 means they're negatively correlated, or if people watch more of one show, it means less of the other one. And a 0 means there's no relationship. So reading down the first column, we can see that Doctor Who is perfectly correlated with itself. Fargo is not correlated with Doctor Who. So people who watch a lot of Doctor Who are no more likely to watch Fargo than people who watch no Doctor Who. We can see there are much stronger correlations for Doctor Who with the other science fiction shows. The next technique is to reorder data, and it's my personal favorite. Now, pretty much all market researchers already do this. You might sort market share data from biggest to smallest, just kind of the classic example. But the idea is much more general than that. Remember my exploratory analyses before? Well, we deleted lots. Now we're going to sort them. We're going to sort by significance. And now I can quickly see that my best, the strongest relationship between purchase intent is with itself, but we can see all of the other questions that are strong predictors, and we can see that age is kind of down here and the TV viewing a lot lower. But, and while that's a great little time saver, the thing that makes me love reordering is diagonalization. When we have two-dimensional tables, we can reorder the rows and columns so that the small numbers are in one corner. You can see this visually shown here. Now, when we do it, it turns out to make patterns really easy to see. And there are only really two types of patterns. There's something called a hierarchy, which is when you can rearrange the rows and columns so all the small numbers in one corner. And then there's something called segmentation, which is where you have two opposing corners containing all of the small values. But let me prove to you with a good example how cool this technique is. Hold on. So, oops, there it is. Sorry, internet moving a bit slowly. Here's my data, the viewing data from before. What I'm going to do is I could rearrange by dragging and dropping the rows to move them so that we have all the diagonals in a corner, but one of my clever colleagues has written this great automatic sorting algorithm where I can just go sort categories by pattern. Now, in this table, it's the same data in the rows and columns. So when I sort the columns, it will also sort the rows. And you'll see that the algorithm's done a reasonably good job. We've got most of our numbers in this bottom left-hand corner, except for the Mandalorian. The algorithm's not quite as good as we are at spotting patterns. I'm just going to drag the Mandalorian down and put it underneath Star Trek Discovery. And now we've got a clear cluster of lots of small numbers in the bottom left-hand corner, and also in the top right corner. And just ignore the sum. It's not that interesting on a table like this. How can we make this even better? Well, the next thing we're going to do is we're going to turn it into a visualization. A heat map is great for tables with lots of data on it. So we started with a monster crosstab with 1,620 numbers. We've now got no numbers. We've reduced them all to an image. That's true data reduction. And notice that we've got a really clear pattern, right? There's this big square up here and there's this big square down here. And these big squares have a meaning. The square down here tells us that the programs that are here are relatively highly correlated with each other. For those technical people, we could have found this by a factor analysis as well if we were able to figure out how to do a factor analysis of a crosstab. But they're grouped together all of the science fiction shows, which makes sense. And you can see here there's a kind of tighter cluster in the middle of the more, shall we say, nerdy science fiction shows, Doctor Who and the Star Trek ones, and the two Star Trek shows, Picard and Star Trek Discovery, are really tightly correlated together. So this all makes heaps of sense, doesn't it? And we have the non-science fiction shows appearing up here. And again, there are some tighter correlations between some of them. I'm also a big fan of decomposing data. A decomposition is when you replace one number with multiple numbers. At first glance, this seems to be the opposite of the idea of data reduction, but stay with me. Sometimes you can use logic to create a decomposition. For example, in business, we split profit up into two components, revenue and cost. And revenue can also be split up in lots of ways. For example, into the number of customers times how much they bought times how much they paid. Returning to the data we've been looking at, let me tidy this up a little. We've got this metric showing the average viewing of The Mandalorian. So this tells us that approximately 70.71 or 71% of programs of Mandalorian programs were viewed by a sample. Now, we can decompose this into two components. The table to the right is showing the percentage of people that have watched one or more episodes, also known as the penetration, and the one to the right of that is showing the average proportion of episodes watched amongst those who watched more than one episode. And this table on the far left is just computed by multiplying together the numbers in these two tables. So that's what a decomposition is. Now, if you look at it, we see something interesting. In our original table, there's a big drop off between Stranger Things and Picard. And so you go, well, The Mandalorian and Stranger Things are really popular and everything else is less popular. Fine. But when we look at the decomposition, we note something really interesting, which is Picard's penetration score. It is lower than Stranger Things, but it's only 21% lower. But it's the average proportion of episodes watching, or the frequency of consuming, to use a more general term we'd use if it was a product, which is vastly low, it's less than half. And so the weakness for Picard is that it's great at getting people to watch it, but once they watch it, they don't watch it nearly as much as the Stranger Things. The Stranger has watched. So it's got okay penetration, but it's got very poor repeat viewing behavior. The most famous decomposition is the seasonal decomposition. This is a case of an algorithmic decomposition. So in the previous example, I used my knowledge of the market to think about how to do the decomposition. Here, I just click a button on the computer or write a line of code, as I did in this case here. And for those of you who are not familiar with it, the idea of a seasonal decomposition is you take your data here, and this is showing levels of carbon emissions in the atmosphere over time, and you split it up. And this one's called an additive decomposition. So it means that this overall data can be viewed as being the sum of the trend, the seasonal component, the noise. And the benefit we get there is when you just look at the raw data, you see it's going up and there's a lot of seasonality very predictably. But when we split up, we start to see little nuances in the data, which we just couldn't see. And in the random noise, we can see there are certain years where they're completely out of whack. And so that allows us to look into them and figure out what they were. Again, that's the goal with the decomposition. But back to our viewing correlations again. So we've got this correlation matrix. We made a great heat map before, but now we're going to apply decomposition to it. And if you've been to many of these webinars before, you're going to know I love a technique called correspondence analysis. Now, this table here is a special kind of table. It's got the same row names as column names. And in the jargon of statistics, this is sometimes called a square table or a square matrix. And so I'm going to visualize it. I'm going into dimension reduction, and I'm going to choose the second of my correspondence analysis, which is a special one for correspondence analysis of a square table. Cool. Now, so the decomposition started with a table of 121 numbers, and in the background, it turned them into 20 numbers that best explain the data and another 80 numbers that just explain marginal things like much weaker patterns or noise, if you like. And we've just plotted the first 20 as coordinates. So Star Trek Discovery is down here, And it's been plotted. You can see the values. It's just showing us the values. It's been plotted on the first 2 dimensions. So we've reduced it down to 20 numbers, which we've then turned into a picture. Now, the way we read this is if 2 shows are closer together, it means that they're correlated. And so we can see here, we've got this cluster of science fiction shows, but the Mandalorian's a little bit different to the rest of them. We've got the non-science fiction shows, but again, You and Fargo are a little bit different. So we've got a more nuanced understanding. And if this was a real world study, we'd go back to look at our table of correlations and try and understand what made these ones special. The last way of reducing data is to use common sense. In practice, this comes down to 3 things. The first is consistency. If a result is not consistent with existing data and theories, it's probably wrong. Second, we apply the smell test. If a result smells fishy, it probably is. There's a rule called Twyman's rule, which says that any result that looks interesting is probably wrong. And this rule, sadly, is usually right. The third secret to applying common sense is to go looking for apes. An ape is an alternative, plausible explanation for the finding. If you can find an ape, then it's appropriate to either get rid of the analysis or prove the ape is wrong. Let's do some examples. Imagine a not very good data scientist is building a predictive model trying to work out what causes the amount of damage that occurs in a fire. And they collect some data, and one of their variables is the number of firemen. And they predict that the more firemen, the more damage to the data, because there's a correlation between the two. Now, the data is actually correct. There is a correlation, but it's what we call a spurious correlation. As the ape says, the real story is that we see the pattern in this data because more firefighters are sent to worse fires. So it's the badness of the fire that determines the number of firefighters, not firefighters turning up causing fires to get bigger. Obvious, right? Let's do a more realistic example of the type that we have to solve in survey analysis. Here we've got a table which is showing the relationship between whether people say they definitely buy our iLog and their attitude to technology. When you look at it, you'll see there's a very clear pattern, which is the more they love technology, the higher their chance that they would say they definitely buy the iLog. And so that leads to the conclusion that the iLog is most appealing amongst technology enthusiasts. Makes sense, right? So it passes the consistency test and the smell test, I think. But can you see an ape? And there is an ape. The ape is this. It could be that we have a response bias. And response biases are perhaps the most common ape in surveys. The idea of this ape, alternative plausible explanation, is that biases in how people answer questions cause certain types of patterns to appear in surveys, in particular correlations. Now, the most classic of the response biases is the yay-saying bias. And this is the idea that there are some people who just like to choose the first option, some people just like to choose the middle option, some people like to choose the last option in the list, regardless of what the question is. Now, if that is the pattern that you have in your data, you would expect to see correlations of this type we've got here. So now we've got 2 explanations for the data. It could be that technology enthusiasts are more likely to buy, or it could just be that we've got a response bias. Now, if you think back, we actually saw that viewing of all of our TV shows before were correlated by and large, and that's consistent with this response bias. So maybe we've really got a response bias issue. How do we test it? Well, the way we test it is we try and find some other data which should show this effect if the response bias is true, but where we wouldn't expect to have any relationship if there's no response bias. And in this survey, we've got a simple example. We can correlate the viewing of Fargo with the intent to buy the iLog, because the Fargo data is in the same data set. Now, if there was a strong correlation, it kind of becomes a bit unlikely that Fargo viewing is related to you wanting to buy the iLog. And fortunately, what we see is the I would definitely not buy it scores, which is the ones we're focusing on, aren't significantly different between depending on frequency of viewing Fargo, telling us that this APE of response bias doesn't seem to be a big factor. So that's great news, isn't it? Now, some people go, oh, but there are significant things. And yeah, you often get little weird significant results on tables. It's just one of those things you've got to get used to. That's why you need to apply common sense. In our resources, you'll find webinars with beginner's guides, more in depth on crosstabs, and lots of advanced topics as well. So I'd encourage you to go to homepage, check out the resources section and see what you can find. And yes, later this week, we will send you a recording of this webinar. Questions, please type any questions you have into the questions field in GoToWebinar and I'll answer them now. A couple of advertisements. In 2 weeks, we'll return to storytelling. So we've looked at how we find the story and we're going to look at how we make it into a really compelling story. That's in 2 weeks. Next week, for those of you who are following on a DIY series on conjoint, we're going to look at the data we collected. We're out of field now, got 1,056 completed interviews from the experimental design that you all helped me create last week. And we're going to start to do the data checking and perform statistical analysis on. Anyway, let's see what questions people have got. Scott, g'day, Scott. What does sum mean in the table of correlations you just showed? Well, that is a surprisingly interesting question. Not surprisingly interesting question. That's a terrible phrase. Sorry, Scott, you're always interesting. Language is dangerous, isn't it? All right, let us go and we'll turn this back into a table. Now, in the raw data, and I'm gonna, with this table here, I'm gonna change it so it's just looking at the summary. So it's showing me here that the average viewing in this data for Fargo is 2, the average for little fires everywhere is 1.9. Now, if we go and look at what that data is, we'll see it's just on a ugly little 6-point scale, and we could maybe put different numbers in here, like this could be put as 0, this could be put as 1, but it doesn't change the conclusions as I talked about before. Now, the sum is literally the sum of all of this data. And so if we look at the raw data of the table, you'll see that indeed the sum is just the sum of the numbers in each row. So returning back to our correlations, we're just correlating the sum of all of the variables with each of the other variables. Now, if you think about that for a while, you realize it has to be correlated with each TV show because the TV show is an input to it. So it's equivalent to having factor analysis with a single factor, or almost equivalent, I should say. James, hi. James says, will a recording be sent? You betcha. Anthony says, really interesting stuff. Thank you, Anthony. How and where do you and the Displayr DIY customers source the survey samples from? Yeah, well, there's lots of places to source survey samples from. There's the wonderful people at Pure Profile, for example. There's the wonderful people at Donata. With the survey that we're doing at the moment, we tend to do them from Qualtrics because we use Qualtrics as our data collection platform. But there are lots of companies out there that provide that as a service. Anyway, that's all the questions we've got, everybody, so you get to escape early. For all of our customers out there, thank you so much for being our customers, and for everybody else, thanks for coming to the webinar. Hopefully you saw something that you thought, oh, I need to buy that software. Go to Displayr.com, book a demo. Someone will take you through things. Anyway, be well now. Bye.